Thank you.
Okay, thank you. It's a little bit different today. I'm going to be talking about some of the work that we did a while ago when I first started in the AFM-IR laboratory in Manchester, really exploring about how the fundamental nanostructure in network polymers exists and how it's formed, but also whether we can relate that to water transport through these coatings and ultimately ion transport and corrosion failure. So the challenge that was originally set to us by AkzoNobel for this piece of work was, can we work out why in an intact clear coating, when we eventually get corrosion failure, why it happens in one particular spot in the absence of a defect. And so as our starting point, we used this Nguyen model, which is it's a really nice model. It's based on a lot of literature, if you go read the paper. But the summary is here. So the idea here is that in network systems, but especially epoxies, there is this intrinsic heterogeneous structure at the nanoscale. And so some of that structure will be more hydrophilic than the rest of it. And that means that we get heterogeneous water uptake into these coatings over time, because we know that these intact coatings tend not to fail immediately in the absence of a defect. So over time, the idea is that these hydrophilic regions, which absorb water, kind of join together and form channels, eventually allowing ion transport to happen through the coating. So this is a really nice model, but there was very little direct evidence for this. So the first thing I decided to look for was this nanostructure. So it turns out the nanostructure in epoxy resins has got a long and pretty contentious history. Beginning way back in the 1950s, we had a lot of electron microscopists saying when we fracture these systems, you can see that there is an internal nanostructure. And the idea was that internally, the proposal is that there were highly cross-linked nodular regions embedded in a lightly cross-linked matrix. And that when you fracture them, the fracture path goes around these nodules, giving you this kind of fracture interface. So that model was widely disputed by polymer chemists and scientists. I've highlighted this paper by Carl Dusek because he makes a very compelling case that epoxies are not two-phase materials, they don't behave like two-phase materials, and that these nodular features must be some kind of imaging artifact. And this is such a compelling paper that when I first approached this, I fully expected to, I thought I will go and use my nice microscope techniques and demonstrate that these systems are actually homogeneous, but it wasn't quite so simple. So later on, more recently, there were also reports using AFM, as that became more widespread, to look at these fracture interfaces. So this is an example from a nice paper by Chris Sagan, where he's used the phase images of fractured epoxy systems to say, yes, there is this nanostructural heterogeneity. But again, there's pushback here as well. So certainly at that time, when you're looking at roughnesses on these kind of length scales with an AFM, certainly if you're tapping too hard, there's every chance that you are actually kind of imaging the end of your tip rather than the real surface. And so there were also responses to this paper saying, nope, that's an imaging artifact as well. Epoxies are homogeneous. So for my system, I was using this model, Epoxy-Phenolic, which was loosely based on the can coating systems we were using at that time. So the same pure chemistry, but obviously stripped down to well-defined ingredients. And what I found when I looked at the fracture interfaces for these is that I slowed the reaction right down by lowering the catalytic content, and then we could actually see this kind of structure developing over the cure time. And the fact that it appeared in both SEM and AFM images was a really strong indication that this structure exists within these resins. Whether or not it correlated to chemical heterogeneity and variations in cross-link density wasn't necessarily clear. Saidi applied at that time, brand new AFM-IR microscope. I'll just quickly run through the technique for anyone who's not familiar with it. So in AFM-IR, we have a standard AFM setup with a probe in contact with your sample surface. And there is also a pulsed, tunable infrared source focused on the sample surface as well. The idea is when the frequency of that instant infrared matches an infrared absorbance, is that the absorbance by your sample causes it to briefly expand in response to that pulse. We can detect that using the laser deflected off the top of the cantilever, and we get these ring down signals in response to those infrared pulses. So what we can do is we can step that instant infrared radiation through the infrared range and get very, very local spectra, or we can hold the infrared at a particular wave number and scan and get chemical images at very high resolution. So these are some examples from our work with corrosion protective paints. So the top one is an image of a silica matting agent embedded in an epoxy coating. And at the bottom we've got paint penetration into rust, where you can just see that the actual coating penetration into the pores really lights up because we're able to image at the correct frequency with the infrared. So to look into this nanostructure, we use very, very thin sections. So at this time, it's really pushing the sensitivity and the resolution capabilities of this microscope to its limits with this work. So we created 50 nanometer thick or 100 nanometer thick sections of the specimen, deposited them onto zinc selenide substrate, and then got local spectra with 50 nanometer spacing across the surface. So here the black spectra are the local infrared spectra collected from the specimen. The red spectrum is the bulk FTIR. You can see that they're a really nice match. The only absorbance that really varied is correlated strongly to the cross-linking mechanism and cross-linking density, and therefore also imaging at those wave numbers. We had evidence that this nanostructure corresponds to local chemical variation and local variations in cross-link density. So then I went on to look at different ways of generating this kind of nanostructural heterogeneity. Looked at very many different systems, varying the stoichiometry, the cure temperature. And what I can say is the only time I was able to get homogeneous resins that appear homogeneous when we create a fracture interface was if I lowered the cross-link density overall substantially, and therefore really compromised any kind of coating performance. So the idea that we could create homogeneous resins and those would be more protective, I think is a bit of a non-starter. There's also been a lot of research activity in this area generally since. There's a really nice, relatively recent paper by Yamamoto illustrating that these kind of areas of heterogeneous cross-linking may actually be instigated by the exothermic epoxyamine, in the case of epoxyamine reaction, which then in turn, because it's giving off heat, encourages like bonds nearby at a molecular level to also cross-link. But having confirmed there is intrinsic chemical heterogeneity at the nanoscale in these systems, we then wanted to look at, well, what happens over this long period of immersion? Can we find any evidence that these kind of hydrophilic channels are developed? So I said, does a pore structure form possibly during water uptake? And is it related to the nanostructure? So again, employing the AFM-IR, I looked at the initial water uptake in a humid environment into these coatings in relation to local cross-linking density, and found that we could relate where the water was taken up very much to the local chemistry. And we do have heterogeneous water uptake at these length scales. But that was kind of, those experiments using humid air are looking at this very short-term water uptake that happens within maybe the first hour or so, and then you reach kind of a pseudo-saturation point. We're more interested in slightly longer-term experiments, so did some in situ FTIR experiments showing that after your initial very rapid water uptake into an epoxy resin, we get this much longer period where you get this gradual increase. It's called non-Fickian diffusion, and it's related generally to the relaxation or rearrangement of the polymer. And it coincides, when we look with the AFM just at the top surface, with deformations in the polymer and the formation of this nanoporous structure on the surface. It's you may have to squint a bit to see on the 7-day one, but it does appear that pores are forming. And when I looked at where water was absorbed onto these kind of porous structures, what you can see is that hopefully in the IR images with the D2O vapor, you can see that those pores really light up when I expose the sample to D2O, because that's where the D2O is absorbing onto. So we're making these hydrophilic pores on the surface of samples. Can't look inside the sample, but you can imagine something similar is going on internally. So this seems to support this idea that maybe we're making hydrophilic channels or similar through the coating. However, I don't have the link between overall long-term water uptake and this initial nanostructure. And as I said, I tried a lot of different things to try and create a homogeneous and a heterogeneous sample to compare. And this is one of the closest. So this is varying the stoichiometry. We can make a more homogeneous or less homogeneous sample, and then look at water uptake. So this is gravimetric experiment. What was interesting here is, so the more homogenously structured excess epoxy sample, which is also less polar, and that's normally considered to govern water uptake, actually took up much more water, and we did some EIS experiments just looking at the time taken to reach a 2-time constant kind of response, and we called that the failure point. And they also failed more readily when we looked at these systems as coatings using EIS. And what that tells me is that actually the water uptake mechanism by these kind of systems is less dependent on the nanostructure or even the polarity, and it seems to be far more dependent on how flexible the coating is and how much it is able to rearrange in response to exposure to or immersion into water over a long period of time. So recently, or relatively more recently, I looked at this system, and here again, we're comparing more homogeneous and less homogeneously structured resins. But for this system, I only varied the cure temperature. So the chemical structure of the resins was kept the same. We did in situ infrared experiments to make sure that the epoxy conversion, the overall degree of cross-linking was kept constant. So these were as similar as they could be, barring the internal structure. Then, to look at water uptake, we've employed DVS. So, because these are very similar, and you're looking at very small changes in the water uptake, gravimetric experiments aren't really accurate enough. So when we have an epoxy resin, water uptake is very, very rapid, but so is drying. So if you take, especially a thin coating, out of solution, pat it dry, and then put it on the balance, you can see it losing water as it's on the balance. So it's not that accurate as a measurement technique. Whereas in DVS, we're holding the system under 90% humidity for several days and accurately measuring the mass change. And when I compare the heterogeneously structured and the homogeneously structured samples, the first cycle of water uptake, you can see that the heterogeneously structured sample seems to take up slightly more water, slightly more quickly on that first cycle. But I think what's interesting here is that on the second cycle, so after we've dried it out again and then we do a second cycle, that difference completely disappears. So, in conclusion, heterogeneous nanostructures seem to be an intrinsic feature of epoxy network polymers, certainly Epoxy-Phenolics and all the epoxy amines I've looked at. As long as there is some degree of cross-linking, we seem to get these kind of structures forming, and they form prior to or during gelation and then are stuck. We know that water uptake proceeds in a heterogeneous manner initially, so that was looking at kind of what happens when you expose these to water vapor. We can see that it's taken up onto the surface of the epoxies in a heterogeneous manner, corresponding to this kind of nanostructure. And then long-term rearrangement during non-Fickian water uptake seems to give us hygroscopic pores on the surface of films. I think the key kind of takeaway from the more recent water uptake work that I've done is that I don't think those two things are linked. So the hygroscopic pores and the potential formation of channels in the film, I think, is not correlated to the actual nanostructure. I think it's far more dependent on the overall degree of cross-linking and the flexibility of the resin structure. That's the end of my presentation for today. I've got tons of co-workers and people at AXO and Manchester and Dresden and Sheffield to acknowledge. That's the end of my talk. I'll take any questions.